Hello students, welcome to physics class. I am Dr.J Babu, Assistant Professor of Physics from Vivekananda Government Degree College. Today we will discuss about the classical and statistical quantum statistics. For this, I am going to share PowerPoint presentation. So in previous video, we discussed about the statistics. Today we will discuss about the classical and quantum statistics. So outline of my presentation is, first I will discuss introduction to classical and quantum statistics, BE Bose-Einstein statistics, FD statistics, Maxwell-Boltzmann distribution law, Bose-Einstein distribution law, Fermi-Dirac distribution law. Finally, I will discuss comparison among Maxwell-Boltzmann, Bose-Einstein, and FD statistics. So, finally, I will discuss about the applications. In previous lecture, we discussed about the statistical mechanics. So, when in statistical mechanics, consider the microstates of the all particles by taking consideration into the microstates and probability theory, statistical methods. By using probability theory and statistical methods, we developed the statistical mechanics. So that here we discuss about the ensemble also. The ensemble is the entity which describes certain values like temperature, volume, and energy. And we discuss of the phase space. It is a six-dimensional space. Apart from the three position coordinates, it also described with the velocity or momentum coordinates. Three position coordinate xyz and velocity coordinates vx, vy, vz, or momentum coordinates px, py, vz. So that the six-dimensional space is called the mu space or phase space. And the combination of phase space is called the tau space. So, but this classical mechanics is explain the all the phenomena, but some phenomena like like other phenomena is failed to explain by the classical mechanics. So that classical mechanics, statistical mechanics can be divided into two parts. One is classical statistics and or Boltzmann statistics, and second one is the quantum statistics. So that the classical statistics utilizes the Maxwell-Boltzmann velocity distribution of particles, whereas quantum statistics utilizes the Bose-Einstein or Fermi-Dirac postulations. Here, classical statistics explain successfully about so many observed phenomena like temperature, pressure, and energy, but it failed to explain several other experimentally observed phenomena such as black body radiation, photoelectric effect, specific at low temperature. So that this is the drawback of classical statistics. To explain this, the new quantum statistics was emphasized by using discrete exchange of energy between systems. And the quantum statistics was first formulated in 1924 by Bose in the deduction of Planck's radiation law by purely statistical reasoning on the basis of certain fundamental assumptions, radically different from those of classical statistics. So, in classical statistics, we use discrete exchange of energy, but here not discrete, not continuous, here some distinct values of energy. So that in the same year, Einstein also used the same principle in evolving the kinetic theory of gases as a substitute for the classical Boltzmann statistics. That is a new quantum statistics known as the Bose-Einstein statistics. And in year 1926, Fermi and Dirac modified the Bose-Einstein statistics using additional principle suggested by Pauli in connection with electronic structure of atoms known as Pauli's exclusion principle, according to which no two electrons having the same set of quantum numbers may be in the same state. In statistical mechanics, this exclusion principle takes the form that two or more phase points cannot be possibly occupy the same phase cell. This led to the recognition for the second kind of quantum statistics called the Fermi-Dirac statistics. Thus, quantum statistics again can be divided into two types. So in Fermi-Dirac statistics, applies the Pauli exclusion principle. According to Pauli exclusion principle, one phase point cannot occupied by the two or more phase points, so that one particle can occupy one cell. One cell cannot occupied by the one or more particles. That is called the Fermi-Dirac statistic. So that look at the picture, the diagram. This is the statistical mechanics. First, we can divide into two parts: classical statistics and quantum statistics. The classical statistics is MB statistics. Again, quantum statistics is divided into two parts, and VE statistics and FD statistics. FD statistics follows the law of Pauli's exclusion principle. So, Bose-Einstein statistics. This applicable to the identical particles. The particles of the whole should be identical, means that it should be a same set of gas, and indistinguishable. We cannot distinguish one particle from the other. That is called the indistinguishable. And zero or integral spin. The spin is either zero or it's a integral multiples of the integral multiples. So that only for this we can apply the Bose-Einstein statistics. These particles, those obey the Bose-Einstein particles are called the bosons. The examples are photons, pi mesons, helium-4 atom, etc. For this, spin should be integral multiples, so that zero are integral multiples, like h cat, 2h cat, 3h cat, like that. But whereas in case of Fermi-Dirac statistics, it is applicable to the identical. Here also all the particles should be identical. And indistinguishable, we cannot distinguish one particle from another particle, all are identical, we cannot distinguish. But the spin should be off integral spin, and also the obeys the Pauli exclusion principle. Then these are called the fermions. So that examples are electrons, neutrons, protons, neutrinos, helium 3 atom, etc. are called the fermions. So that the main difference between the Bose-Einstein statistics, Fermi-Dirac statistics is Bose-Einstein statistics applies for the zero or integral spin of the particles, but Fermi-Dirac statistics apply the off integral spin of the particles. And Fermi-Dirac statistics obeys the Pauli exclusion principle. And the main difference between the classical and quantum statistic is classical statistic, the particle are not identical, not distinguishable. They are individually recognizable and they are distinguishable. Each particle likely to be in one cell. So that we can discuss about the how these cells will be occupied by the particles. So that in quantum statistics, each particle is distinguishable. For example, particle A is different from the particle B. They are not same. Maybe they are identical, but not same. So that the individuality is maintained in classical mechanics. They are not, they may be distinguishable. We can distinguish A particle from B so that they are recognizable individually, hence the particle are distinguishable. Even though they are identical but distinguishable. And each particle is likely to be one cell, as in this means that classical statistics, each or both particles can occupy one of the three cells. So that if you see the classical mechanics, the arrangement of particles is the particles are identical but distinguishable, so that A is different from B particle. They occupy, both particles can occupy one cell, any of one cell, like both A, B particles occupy first cell or second cell or third cell, or like that a particle A occupies one cell and B occupies other cell. Here also B occupies first cell, A occupies second cell, or A occupies first cell, B occupies third cell. Like this arrangement is also possible, or we can get like this arrangement also. So that here we can get three set of arrangements. So that 3 total 9 ways of occupying the particles of the cells in classical mechanics. Coming to the Bose-Einstein statistics, the particles lose their identity, their individuality. They are indistinguishable. We cannot separate the particles. We cannot recognize the particle individually. All particles are identical or indistinguishable, so that A particle is same with B. So that B is equal to A or A is equal to B. So that we can concentrate our attention on the cell rather than the individual particle. So that according to Bose-Einstein statistic, both particles can occupy one cell or they can occupy different cells. So that here that both particles A occupy the first cell, here second cell, here third cell. But and also possible they occupy the different cells individually. A occupy this one like this, like so. That's in Bose-Einstein statistics. There are three ways of possibility to occupy the self. But coming to Fermi-Dirac statistics, which obeys the Pauli exclusion principle, cannot occupy the cannot occupy the one cell, so that cannot occupy the one cell, so that here Pauli exclusion principle, according to Pauli exclusion principle, one cell cannot occupy with the two atoms. They occupy the individual cells. A should occupy one cell and another particle occupy the another cell. Cannot accommodate both particle in a single cell. So that only three possible ways of accommodating the particles in according to the Fermi Dirac statistics. So that is why this is the case we can arrangement of these particles will take place. Now we can move to the Maxwell-Boltzmann statistics. The Maxwell-Boltzmann statistics were developed on the basis of the classical mechanics, classical or discrete energy level. To explain the Maxwell-Boltzmann distribution law, now you can consider n number of particles. They are identical but distinguished particles. Each particle is described by a set of position and momentum coordinates, and therefore an energy is associated with it. Any energy eigenvalue of the system is a sum of single particle energies called levels. You can see the levels here. As the values of position and momentum can take continuous values, because here we can take according to Maxwell-Boltzmann distribution law, the energy is continuous, it's discrete, not the fixed values, it's continuous values. These levels from continuum, let us divide the spectrum into groups like G1, G2, G3. This is this level continuously from year to year. This is called Z1, this is Z2, this is G3. Like that, this is GK. So each group is called a cell. Here, this is the one cell, second cell, third cell, like that. Each group of level in spectrum is called cell, and having the energies like epsilon 1, epsilon 2, epsilon 3, like that, epsilon k. So that here we are considering the spectrum into groups like G1, G2, G3 are cells, and they are having the energies epsilon 1, epsilon 2, epsilon 3 are the cells having their respective cells. And let N1, N2, dash, 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 Nk be the occupation number of cells G1, G2, G3, and Gk. So that here we are considering the three essential parts. We can say one is cells represented by the G1, G2, G3, Gk. Second one is the energy. Energy of the first cell is epsilon 1, epsilon 2, epsilon 3, epsilon k. And third is number of cells, number of particles occupying the cells, that is occupation number like N1, N2, N3, dash, 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 Nk. So if you consider these three parameters, We can go through the Maxwell-Boltzmann distribution law very easily. So here the conditions in Maxwell-Boltzmann statistics are: number one, particles are similar, identical, but distinguishable, and there are no symmetry restrictions. Here we cannot apply any symmetry restrictions, no symmetry restrictions at all, so that particles are similar and distinguishable, no symmetry restrictions are applied. Each second point, each eigenstate of ith group contains 0, 1, 2, dash, 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 Ni particles. So that each cell may contain 0 particles or contain 1 particle, 2 particles, or any number of particles. That is the second point, second condition. And third condition is total number of particles in the entire system is always constant. So that we are taking the fixed amount of particles, so that the number of particles in each cell may vary, but the total number of particles should be constant. That is, capital N is equal to N1 plus N2 plus dash 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 Nk. Maybe the number of particles in self may vary, but total number is constant, that is capital N is constant, or summation I equal to 1 to k Ni is equal to constant. And delta N is equal to, we can say, delta N1 plus delta N2 plus delta N3 plus dash 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 delta Nk is 0. So, because N is the constant value, so that differentiation, partial differentiation of the N must be 0. Therefore, the summation of I equal to 1 to k delta Ni is equal to 0. The sum of, this is the equation 1, we can take summation of I equal to 1 to k delta Ni is equal to 0. And now we can consider the energies. The energy of each cell we can get by multiplying the number of particles occupying that cell into the energy of that cell gives the total energy of the each cell. So that the energy of the first cell is equal to epsilon 1 n1. Second cell epsilon 2 and the number of particles in that cell n2. Like that, epsilon 3 n3, epsilon I ni, epsilon k nk. If you sum all the energies, that is capital E is equal to epsilon I ni plus epsilon 2 n2, epsilon 3 n3 plus dash 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 epsilon I ni plus epsilon k nk is equal to constant. Here also the total energy of the whole system, capital E is equal to constant. If you take the derivative, partial derivation, delta E is equal to epsilon I delta ni plus epsilon 2 delta n2 plus epsilon 3 delta n3 plus dash dash epsilon I delta ni plus delta epsilon k delta nk is equal to 0. Therefore, summation of I is equal to 1 to k epsilon I delta ni is equal to 0. This is equation number 2. These are the very simple equations, equation 1 and equation 2. Equation 1 is about the total number of particles and equation 2 is total energy. Now, in this distribution, the gas molecules are distinguishable and they are divided into groups, and Ni particles, N1 molecules in the first state, N2 molecules in the second state. Already we discussed, we can we can arrange, these particles may occupy any cells, any number of particles can occupy any cells, so that the number of ways in which Ni particles, N1 molecules out of total N molecules may fall in the first state are. So that now the intention is how the first state will be filled. The first state N1 can be filled out of total number of N molecules in the following way. So out of total number of N, the N1 can be filled by the combination of NC and 1. NC and 1 is equal to n factorial by n1 factorial into n minus n1 factorial. This is the way how the levels, this is the way how the first level will be filled by the total number of the particles. The total number of the particles are capital N. Out of the capital N, the first cell N1 can be N1 particles, N1 molecules out of total N molecules may fall in the first state. Therefore, NC N1 is equal to n factorial by N1 factorial into n minus n1 factorial. Now the remaining particles are capital N minus n1. Already n1 particles are filled by the first level, so that the remaining particles are capital N minus n1. Among the capital N minus n1, N2 particles are occupied the second cell, so that the number of ways in which any N2 molecules out of remaining N minus N1 molecules can be placed in the second state as N minus N1 C N2 is equal to N minus N1 factorial by N2 factorial into N minus N1 minus N2 factorial. Like this, the remaining particles are, if you want to fill the N3 state, the remaining particles are N minus N1 minus N2. So that among the remaining particles N minus N1 minus N2, N3 particles are occupied the third cell in the following way. So that N minus N1 minus N2 C N3 is equal to N minus N1 N2 factorial by N2 factorial into n minus n1 minus n2 minus n3 factorial. Like that, so on. This will continue up to nk molecules for the kth state. If you combine all the total number of ways in which molecules in different states may be exchanged, leaving the total number in each state is fixed, we can get that we have to multiply all these ways, all these equations, so that we will get equation number 3, that is equal to n factorial by n1 n1 factorial n2 factorial dash 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 nk factorial. So the equation 3 represents the thermodynamic probability of the distribution. Now let each group, each cell Gi be described by the Gi elementary wave function and therefore Gi energy levels. Consider the ith group. The particles are accommodated in Gi different levels. The first molecule of Ni can be accommodated in any of the GI levels, which can be done in GI ways. The second molecule can also be accommodated in GI ways because there is no restriction on this molecule. In this manner, all the ways total in the all the Ni molecules can be occupied in GI levels in GI factor GI to the power of Ni ways. Therefore, priori probability that Ni molecules occupying simultaneously ith level is GI to the power of Ni. The number of distinguishable ways which n molecules total, this is GI to the power of Ni ways. The prior probability of any particle distribution of n balls among the case states such that Ni molecules occupying the first state, N2 molecules second state, like that, so on. GI to the power of GI to the power of G N1, GI to the power of N2, GI to the power of Ni dash dash Gk to the power of Nk. The number of distinguishable ways in which capital N molecules can be distributed among the possible energy levels is P is equal to Ni factorial by N1 factorial, N2 factorial, Nk factorial into the 6 point. This is 6.3 into 6.4, equation 6.3, equation 3 into equation 4, we will get the P. That is equal to Ni factorial pi I equal to 1 to Gi to the power of Ni by Ni factorial. The probability of the given state total is equal to now this one. Now we apply the natural logarithm for this equation. We will get ln p is equal to ln n factorial minus summation ln ni factorial plus summation ni log gn. By using the Stirling theorem, ln ni factorial is equal to n ln n minus n. If you apply the Stirling equation for this above equation, we will get like this. So that this is Stirling approximation, so that we will get the equation number 7. For the most probable distribution, P is maximum subject to the restriction that total number of particles capital N and the total energy E are the constants. From equation 7, this P is maximum, so that here we will get it is equal to 0 since delta Ni is equal to 0. Ni 0, Ni 0, Ni 0. So that ln P maximum is equal to 0. We will get this is equal to 0. So comparing the from equation 1 and 2 can be incorporated in equation 6.8, making use of Lagrange method of undetermined multiples. We will get equation 1 by minus alpha and equation 2 by minus beta, and adding to equation H, we will get this one. So as delta Ni are independent variables, for the validity of the last equation, the quantity within the brackets must always be 0. This must be always be 0. Each value of it. Therefore, this within the bracket we are equating to 0. We will get Ni is equal to Gi e to the power of minus alpha into e to the power of minus beta epsilon I. Therefore, Ni is equal to Gi by exponential alpha plus beta epsilon I. This is the Maxwell-Boltzmann distribution law. So, by this way, we can derive this Maxwell distribution law. Here, we can replace the beta is equal to 1 by kt. Therefore, we can get Ni is equal to Gi by exponential alpha plus epsilon I by kT. So the number of molecules per cell decreases exponentially with the energy epsilon I associated with the cell. This means that low energy cell contains more molecules than the high energy cell. If you go into high energy state, the molecules containing the high energy state are less, but low energy state are very occupied with very number of particles, more number of particles. This is about the Maxwell-Boltzmann distribution law. Now we will discuss about the Bose-Einstein distribution law. The Bose-Einstein distribution law, coming to the Bose-Einstein distribution, this he assumed that like here the particles are identical but indistinguishable from each other, whereas in empirical statistics particles are distinguishable. Here, if two particles interchange their position or energy state, new state is generated in case of Maxwell-Boltzmann statistic. But in case of Bose-Einstein statistics, particles are indistinguishable. The complete set of eigenfunctions for such a system are symmetric under an interchange of any pair of particle coordinates. So that is applicable to the only zero or integral pins like 0, 1h ket, 2h ket, 3h ket, like that. And here, based on some conditions, this was developed. The first one is the particles are indistinguishable from each other, so that there is no distinction between the different ways in which Ni particles can be chosen. Second, each cell or subcell of ith quantum state may contain 0, 1, 2 Ni identical particles. Number 3, the sum of energies of all the particles in the different groups taken together constitute the total energy of the system. So that particles are in subcell 1, 1 in subcells 2, or 0 in subcell 3, like that any number can occupy the any cell. So that according to that, if all the balls labeled irrespective of their color with numbers 1, 2, 3, dash dash Ni plus Gi minus 1, the number of permutations is Ni plus Gi minus 1 into factorial. Therefore, in containing these permutation have to be eliminated. The number of distinct distribution of particle for state of energy E1, Ei is equal to Ni plus Gi minus 1 factorial by Ni factorial into Gi minus 1 factorial. Similarly, the expression will be for the various other quantum states. Therefore, the total number of ways in which Ni particle can be assigned to the level with energy epsilon 1 and N2 with the epsilon 2. Like that, so on, we can get the product of all these energies, so that the summation of Ni plus Gi minus 1 factorial by Ni minus Gi minus 1 factorial. Where Ni, Gi are large numbers, hence we can neglect 1 in the above expression, so that we will get this one. By applying the Stirling approximation for this equation, we will get like this by taking ln and applying the Stirling approximation. Here we will get this equation. Here G is not subject to variation and Gi is not subject to variation, and Ni varies continuously. So that for most probable distribution, delta W maximum is equal to 0. So that differentiating this equation, 6.28 equation, we will get this one. Here, because of delta Ni is equal to 0, this we will get 0. Hence, 2.8 becomes delta ln omega maximum is equal to this one. But the system satisfies the following condition. Total number of particles is 0 and total number of energy is 0. Therefore, delta Ni is equal to 0. Because of constant, derivative of constant is 0. Energy is also constant, derivative of total energy 0. So multiplying this equation with minus alpha, first this equation with minus alpha and second equation with minus beta, and adding to the equation 6.29, we will get sigma is equal to ln Ni plus Gi minus ln Ni minus alpha minus beta epsilon into delta Ni is equal to 0. The variations delta Ni are independent of each other, hence we will get this one is equal to 0. Therefore, Ni is equal to Gi by e to the power of alpha plus beta epsilon minus 1. This is the known as the Bose-Einstein distribution law. This represents the most probable distribution of the particles among the various energy level for a system obeying the Bose-Einstein statistics. So that here we will get the minus 1. This you have to remember. Ni is equal to Gi by e to the power of alpha plus epsilon I by kT, or e to the power of e alpha plus beta epsilon I minus 1, where beta is equal to 1 by kT. This is the final equation you have to remember. Coming to the Fermi-Dirac distribution law, here also Fermi-Dirac distribution also the particles are identical and indistinguishable. As we discussed earlier, this obeys the Pauli exclusion principle. No two electrons in atom have same energy state. Only one particle can occupy in a single energy state. In BE statistic, two particles may occupy one cell, but here no two electrons in an atom can occupy. Only one particle can occupy one cell. No two atoms cannot occupy one cell. Because of this Pauli exclusion principle, this is applicable to only half-odd integral spin like half h cat, 3 by 2 h cat, 5 by 2 h cat, like electron, proton and neutron. Here the conditions are for Fermi-Dirac statistics, that particles are distinguishable from each other, so that there is no distinction between different ways in which Ni particles can be chosen. Second, each cell may contain 0 or Ni particles. Obviously, Gi must be greater than or equal to Ni. The sum of energies of all particles in different quantum groups taken together constitute the total energy of the system. So that these are the conditions. Now, here each cell may have one particle. Now, the distribution of Ni particles among Gi states or subcells may be done in the following way. The ith cell to having Gi subcell with Gi minus 1 partitions, so that we easily find that first particle can be put in any one of the ith subcells in Gi ways. According to Pauli exclusion principle, no more particles can be assigned to the filled state. The second particle can be put in the next Gi minus 1 subcells remaining the first cell in Gi minus 1 ways, and so on. Therefore, number of ways in which Ni particles can be assigned to the Gi states is Gi into Gi minus 1 into Gi minus 2 dash Gi minus Ni minus 1, which is equal to Gi factorial by Gi minus Ni factorial. Further, since the particles are indistinguishable, it is not possible to detect any difference between Ni particles or reshuffled among themselves. This is possible in Ni different ways. Thus, the total number of different and distinguishable ways is Gi factorial by Ni factorial into Gi minus Ni factorial. So that the total number of different ways getting the distribution N1, N2, N3, etc. among the various energy levels, epsilon 1, epsilon 2, epsilon 3 respectively, can be obtained by multiplying various terms in the same state. Thus, the thermodynamic probability of Fermi-Dirac distribution is given by W is equal to summation of I. This is summation of I Gi factorial by Ni factorial into Gi minus Ni factorial. From this, like Bose-Einstein statistics, just you apply this Stirling approximation, apply the conditions like delta n omega maximum is equal to 0, but here delta Ni is equal to 0 and total number of particles is constant. Here also total energy is equal, so that summation epsilon I delta N is equal, as the total number of particles and the total energy of the system should remain constant, so that the derivative is 0. Here also by multiplying minus alpha with this equation and minus beta for this equation, we will get like this. As per the variation in delta Ni are independent of each other, we get this one, so that here we will get Ni is equal to Gi by e to the power of alpha e to the power of beta epsilon I plus 1. In this Fermi-Dirac statistic, we will get the plus 1. In that, minus 1. In MB statistics, there is no plus 1 and minus 1. So that we have to remember for the entrance examination point of view. We should not confuse with the MB statistics, BE statistics and FD statistics. In FD statistics, we will get plus 1 in denominator, and here like that we will get. So that now we will compare these statistics. Boltzmann statistics, as you know, distinguishable. Only particles are taken into consideration. Here indistinguishable. Quantum states are taken into consideration. Here also indistinguishable quantum states are taken into consideration. Here there is no restriction on the number of particles in a given state. Here only one particle in Fermi-Dirac, one particle in one state. Here also no restriction, number of particles in a given state. This is applicable to ideal gas. This is applicable to electron and elementary particles. If Bose-Einstein statistics apply to photons and symmetrical particles. Internal energy of ideal gas molecules at absolute zero is taken as 0. Here, even absolute temperature, energy is not 0. The energy at absolute temperature is taken as 0. At high temperature, Bose-Einstein Fermi-Dirac statistic approaches to MB statistics. At high temperature, Fermi-Dirac distribution approaches to MB statistics. At high temperature, Bose-Einstein distribution approaches to MB statistics. Here, as I said, the most probable distribution is given by f to the f function of epsilon is equal to 1 by exponential alpha plus beta epsilon I. In Fermi-Dirac statistics, plus 1. In MB statistics, B statistics, minus 1. It can be interpret many observable phenomena like temperature, pressure, and energy. It could give an explanation for specific radiation. It could explain the phenomena of black body radiation. And this Maxwell-Boltzmann statistics apply for perfect gas lead to PV is equal to RT. FD gas higher pressure than that given by PV is equal to RT. BE gas has a lesser pressure than that given by PV is equal to RT. So in the examination, the long questions will definitely come. Thank you for watching my entire lecture. So in the examination, we will get the long questions from this one. First, explain the MB statistics or explain the Maxwell-Boltzmann distribution law or Bose-Einstein distribution law or FD distribution law. Each uh, will come for the long question or may come comparison of these three distribution functions. So that if you go through this video, you are able to you are able to write the answers for these questions. Thank you for watching my video. If you like my video, please subscribe my channel Dr. J. Babu to get the subsequent notification. Thank you.